Thank you so much for your time and efforts. And today I'm going to tell you about a heuristic algorithm that reduces the CNOT count in Clifford T circuits on connectivity constrained architectures, such as the noisy intermediate scale quantum computing devices. Well, in quantum compilation, we have to translate an algorithm into a set of elementary quantum gates. And Clifford T gate set is a set of very well-studied gates that is universal and is well-suited for fault-tolerant quantum computing. Now, when we are mapping the circuit into the physical layers, we have to consider numerous constraints imposed by the underlying architectures. For example, the connectivity of qubits will restrict the multi-qubit operations to only the adjacent qubits. Now, as a recap, Clifford T circuits are quantum circuits over the 2-qubit NOT CNOT gate and the Hadamard gate, the phase shift T and S gate, and the Pauli operators NOT Y and Z gate. Now, for example, when CNOT gate is acting on a control and a target, when the control is 0, which is not fired, then it is just acting as a wire. And if it is not, if it is equal to 1, then we'll flip the gate, the state of the target bit, as you can see here. Now, for the Y, S, Z, and T gate, they are going to have an added phase to the state, as you can see, where this phase is just a power of omega, where omega is an eighth root of unity, right? Now, because we're considering the connectivity constraint, we use the connectivity graph to represent this constraint. For every qubit, we map it into a physical position. So here, note that we're considering the trivial map, meaning that logical qubit 1 is mapped to physical qubit 1, which correspond to vertex 1 in our graph. And when 2 qubits are adjacent, it means there is an edge. So when the CNOT, so basically when only 2 qubits are adjacent, there's an edge between them, we can apply the CNOT on them. And in our research, we're interested only in the simple undirected connected graphs. So because we want to make sure that the connectivity constraint is respected, one naive solution would be we use a bunch of swap gates to place the logical qubits to admissible physical positions so that now they are adjacent. So for example, let's say we're having this 9-qubit grid where 1 and 9 are not adjacent. But if we want to perform a CNOT gate on the 1 and 9 qubits, we want to take the shortest path in this graph between 1 and 9, which is highlighted by this red line here. And then we're going to place a bunch of swap gates along the path. For example, you can see that we have swapped 1 and 2 and 1 and 5, etc. So eventually, when the first qubit and the 9th qubit are placed on this adjacent 2 wires, which is the 5th and 8th wire, then we can apply the CNOT gate. And after that, we place the swap gates to put those logical values back to the initial position. But the problem of doing this is that even though we are considering the shortest path between these 2 qubits, then it still requires 6 times of the shortest path length. Well, now, if we think about this like linear topology, right? Like let's say we have an extreme case where 2 qubits are, one is at the top, the other one is at the bottom of this topology, then our this naive solution will entail significant number of CNOT explosion. So what we want to do is there a way to resynthesize our Clifford T circuits while respecting the connectivity constraint and reduce the CNOT explosion? So before doing this, let me tell you some of the technologies that we're going to use. So firstly, we use what is called the Steiner Tree problem reduction. And in computer science, Steiner Tree problem is NP hard. And people develop a bunch of approximate synthesis solution to this problem. And we're going to use it to develop our algorithm. We are also inspired by the linear reversible circuit synthesis and the parity network synthesis as proposed by the following authors listed below. Okay, so now let me tell you what is a Steiner tree. You can consider it as a variation of the minimal spanning tree. Now let's say we have a graph and you give me a subset of its vertices. My goal is to find a set of edges in this graph that connects all of the vertices such that there's no cycle and we have the minimal number of edge count. For example, here, G is a simple undirected connected graph where we have 12 qubits, 12 vertices. And 1, 6, 7, 11 are the given vertices, and we also call them as the terminal nodes. On the right, you can see a solution to the Steiner tree problem where all of the intermediary nodes are used to connect these terminal nodes, and we call them as the Steiner nodes. And know that here, an optimal solution to the Steiner tree problem may not be unique, so we can have variations of it. With this in mind, we're ready to define our slice and build technique. So what we do is we first taking an input, that is a Clifford plus T circuit, and we partition it based on the locality of the Hadamard gates. And then we'll get a subset, or like a set of subcircuits composed of only the CNOT gate, phase shift gate, and the Pauli gate. So what we do is we're going to resynthesize the slice portions so that the connectivity is respected and the CNOT count is reduced. So for example, let's say we have this input circuit. So we first massage the circuit so that every gate is occupied precisely one time slice. Now, by traversing the circuit from left to right, we're able to get a bunch of subcircuits, as you can see here. And this leads us to the build technique. So what we do is, well, for each circuit over CNOT, phase shifts, and the Pauli gates, we calculate a phase polynomial, P, and overall linear transformation, A slice. Now, I apologize for the terminology here, but you'll soon understand what do I mean here. But basically, this slice is served as a bird's eye view to show you what's going on and what is behind our method. Now, with this phase polynomial, we're going to synthesize a phase polynomial network, which is just a circuit that realizes this parity terms and use this algorithm. And with this in mind, we have already realized part of the linear transformation that is given by the initial input, right? So what we do is we calculate the residual linear transformation by taking the inverse multiplication of the initial matrix. And then we can perform a linear reversible circuit synthesis over the CNOT and NOT gate that realize this bolded A. And we use the linear transformation synthesis as illustrated here. All right, so let's start with a simple example that we are synthesizing a circuit over the CNOT gate and the NOT gate. So suppose we have an n-qubit circuit. So since this circuit is composed of only the CNOT and NOT gates, we can derive an overall linear transformation that is represented by an augmented matrix. And here, this matrix is of dimension n times n plus 1. For example, below you can see a 4-qubit circuit, and after the state evolution analysis, you'll see that the output has the following states, right? Now, what we do is, well, for every output state, we use a row to represent it. Now, in the right, you can see that this A is an augmented matrix where every column represents the initial state variable, x1 to x4, and the last column represents the bit flip. So let's say if we're looking at the second wire here, it is transformed from x2 to x1 XOR x2 XOR 1. Now, if you look at the second row here, the first and the second position is being flipped to 1, and the third and the fourth position is unchanged. Now, if you look at all of the bit flip, you'll see that the last column precisely registered what happens to this state. So the idea is like this. Now recall that if we're given a circuit that has no gate at all, right? We actually have an identity matrix with an all zero column. So the idea is we're using the reverse engineering to apply a sequence of NOT gates and CNOT gates that will transform this identity matrix to the targeted circuit. So firstly, we apply the NOT gate to the corresponding position, and then we'll carry out an analog of Gaussian elimination. And throughout this process, we'll use the Steiner tree to incorporate the connectivity constraints of the underlying hardware architectures. For example, let's say here we are having this 6-qubit circuit, and the connectivity constraint is like a grid. And we first we first register the linear transformation in this augmented matrix, and we're eliminating the last column since they are just like all zeros or all ones. And what we do is we start from the leftmost column, and by fixing this column to a state where all of the position beneath the diagonal position is 0, then we will move on to the next one, because this will allow us to essentially transform the input matrix A into a upper triangular form. And to be more precise, let's look at it like the first column here. It has 1, 3, 4, and 5 has 1, right? So correspondingly, the terminal nodes in the Steiner tree has this 1, 3, 4, and 5. And this gives us the Steiner tree. And by doing the breadth first search, or like the breadth first traversal of the Steiner tree, we can further separate it into 3 subtrees. And by starting from the last subtrees, we're performing a sequence of well-defined row operations that will give us a sequence of CNOT that will give the corresponding row operations as shown on the next page. So what we do is as follows. For every subgraph, our goal is to propagate 1 from the root node to the leaf node while leaving the intermediary node's parity unchanged. Because if that's possible, then we can just cancel out 1 at the leaf node. And then because we're always starting from the last subtree, so eventually we'll only have 1, 1 that is in the pivot, is like our diagonal position, and every other terminal nodes being set to 0. And by traversing the subtrees, we were able to concatenate a sequence of CNOT gates, and that realizes the first column. And note that here, whenever we are applying a CNOT gate, we have this control, which is J, and the target is I. And correspondingly, it means the row J is being added to row I, and which actually makes sense if you think about the CNOT operation. Now, by iteratively go through all of the columns, we have this upper triangular form. And this leads us to the second step. That is, we are transposing the upper triangular form. So we will now have a lower triangular form. And our goal is to reduce this form to the identity. So note that here we are also performing an analog of Gaussian elimination. We are also performing row operations. But because we're working with a transpose matrix, we need to be very careful about the control bit and target bit assignment. So as usual, we start from the leftmost column and we go all the way to the rightmost column until we get to an identity. And because we want to protect the well-formed, right? Like we don't want to mess up the upper, like the upper values. So a row should always be sorted with a row of a lower index. And if not, then we will apply a correction procedure after all of the subtrees are being traversed. So by doing this, we're able to find a decomposition of our circuit, or like of our linear transformation over the CNOT and NOT gate while respecting the connectivity constraint. But now you may wonder, what if we have a circuit over a phase gate? Well, the phase gate here just means a power of like omega, right? So we have a T gate, T dagger, S dagger, Y, and Z. And know that here, when the T gate is being applied to a state, we do not change its state, but actually the phase. So this means if you're looking at this linear or like this circuit composed of CNOT gate and the T gate, you'll see that the linear transformation at the end remains actually unchanged. It's still like this state evolution analysis result. But if we analyze the intermediary states, you'll see that after applying every T gate, we'll have a change of state or like an edit phase to the corresponding qubit. Note that here I'm using T1 to T5 to represent, like to distinguish different T gates, but they are just like, a power of omega or the 7th power of omega, as you can see here. Now, in 2014, Amy et al. Demonstrated a very nice result. In their paper, they defined something called the phase polynomial network, and they characterized a circuit over the CNOT, NOT, and T gate. So what we do is as follows. They first derive a matrix A that represents the linear reversible function that you can see from the output. And then they collect all of the parity terms from the added phase, and they call it as a phase polynomial set. And finally, they define a phase polynomial network that in our context is a 4-qubit circuit over the CNOT, NOT, and T gate, such that every parity terms is realized with the appropriate phase gate. And this leads us to the phase polynomial network synthesis. So the first step is, well, given a circuit, we want to first calculate the parity network matrix M to represent the parity terms. And I'll show you later what do I mean. And with that in mind, we have a Steiner tree to incorporate the connectivity constraints. And by synthesizing a circuit over the CNOT and NOT gate, we're able to realize all of these parity terms in an efficient way. And finally, because if you look back, you'll see that the phase polynomial set also register the coefficients, right? So based on the coefficients and the position of qubit, we're able to assign this phase gate to the state. Now, in terms of this matrix N that incorporate or like register the parity terms, we define as follows. So N is a matrix that where every column represent a parity term, as you can see here. So now we have 7 parity terms in P, so there are 7 columns. And the first 6 and since here we have 6 qubits, right? So the first 6 qubits represent the parities. So as you can see, if we have x1s or x4s or x5, then the first, 4th, and 5th positions are flipped, and everything else is 0. And we use the second to last row to represent the bit flip. So if you look at all of the parity terms here, you'll see that whenever there's 1, the corresponding position in this row will have 1 in there. And finally, we use the last row to represent the coefficients. And this will help us to reconstruct our T gate and the phase gates after we have all of the parity terms realized. Okay, all right. So now, after doing this synthesis algorithm design, we implement it in Java and also simulate the benchmark and random circuits based on the 5 popular architectures, as you can see below. As the result, we show that for every architecture, our algorithm performed much better than a naive solution. So for example, if you look at the second column here, this shows the number of qubits that come with this architecture, and the third column display the number of CNOT counts. That is the initial one, regardless of the connectivity constraint. Now, if we're doing the swap template, you will see the significant explosion of CNOT count. However, if you're using the slice and build technique, you could see that the increment or like the improvement of the CNOT count is actually quite obvious. Moreover, we know that as the circuit size become larger, the CNOT count become more, and also the architecture become more complicated, our algorithm also scales very well. It means that if you go further away, you'll see that our algorithm still outperform the naive solution in terms of the increment in the CNOT count. And if you look at the time complexity here, you see that our algorithm is also working in a very efficient manner. All right, so to sum up, in this work, we designed a heuristic algorithm that reduces the CNOT count in Clifford T circuits while accounting for the connectivity constraint, which is specified by the connectivity graph. It's possible that we can improve our results by optimizing the initial mapping from the logical qubits to physical qubits, because here we are just understanding the performance of our method as a baseline algorithm. And finally, we actually, this is a question that comes from like a lot of the audience, and then we are hoping to rigorously benchmark against other compilers such as the TKIT by CQC and the Qiskit by IBM to see how exactly our algorithm is compared to the state of art quantum compilers. And that's it. Thank you.